Hi, welcome to the third webinar in this three-part series jointly produced by Google and Intel. My name is Kirat Pandya, and I have with me a guest from Intel.
Thank you, Kiran. I'm Sundar Subramaniam. I'm a technology evangelist at Intel. And today we are going to be talking about ML side of things. At the end of the session, we'll also do a Q&A. So please log in using your Google account to submit any questions.
Hello, and welcome to the third and final webinar in our series. My name is Martin Kronberg, and I am a technical evangelist with Intel.
Hi, and I'm Kirat Pandya, technology lead for machine learning for partnerships at Google.
In the previous two webinars, we looked at how to collect and send data using our gateway, how to query that data when it gets into GCP using BigQuery, and then finally how to visualize the results in Data Studio. Now, in this webinar, we're going to show you how to use that data to train a predictive machine learning model.
All right, so how are we going to get, what's the story of this webinar, right? So we're going to start with talking about machine learning on Google Cloud, right? The high-level tools that we provide to help you build your models. Next, we're going to talk about the actual nitty-gritty of building a model, TensorFlow, the math behind it, all of that. And then finally, I'm going to walk you through a code demo where we sort of walk through the code that takes to build a model. And then we're going to show you both hosting the model in the cloud as well as on the edge on IoT devices and gateways, right where things are happening, if you will. At this point, you're probably thinking, well, I have the right equipment under my desk. I can start building a model here. And you're absolutely right. However, when you get to building a model at scale to solve real business problems, your models are going to be large. And what you're going to need is access to thousands of cores of compute to go train this model, right? You're going to need tons and tons of memory and CPU to go make that happen. And what Google Cloud does is we're very good at being able to provision thousands of cores in very short amounts of time, seconds at most, right? To go build these models, and we only bill you by the minute. So what ends up happening is instead of you having to worry about how am I going to spool up a cluster and manage all of this, we take care of that for you. So instead of planning out your budgets for the next 3 years, how much does my data science team need in terms of compute? You can just sort of use it as necessary and get access to effectively supercomputer levels of performance. Now that we're talking about building a ML model, the start of this journey is data. You're going to need tons and tons of data to build models. There are some models that can go off of small data sets. There are some models that need large data sets to build. The piece of advice I would give here is don't start a journey of gathering data first. Start by asking a business question. What is it that I want to solve? From there, go to your data sets, go to your teams that manage your data, and make sure you have your data that you already have collected, cleaned up, where it's generally understood. There's no sort of random edge cases in your data. Start with that, right? The data is everything. And companies that know how to leverage this data will get ahead, and companies that don't will fall behind. Like every large IPO that we're seeing happen in these last few years has machine learning and the utilization of the data they've collected as a pillar of the value prop of that company.
Right, well, like Kirat just said, data is really everything when it comes to machine learning. And in fact, when we're talking about training a neural network, we're going to need a lot of data. So before moving on, I kind of want to talk about how you, as a developer, can use Intel IoT hardware and software to gather all the data that we're going to need for our training. So in this demo, we're looking at a use case of monitoring 3 environmental variables in order to detect anomalies in that data. We're gathering temperature, sound, and light environmental data using 3 sensors. Gathering and analyzing this kind of environmental data can be extremely useful in many different commercial sectors. So from monitoring a manufacturing process to a smart building's HVAC system, or even keeping track of individual workers' biometrics. And what we want to do here is create a prototype system which can be applicable to all of these and really any other application. So in order to gather the data, we're using these Grow prototype sensors. And these sensors are meant for quickly being able to prototype an IoT project. They have these sockets here, which get 2 sensor pins, a power and a ground, And that basically means that you can use them without having to breadboard or solder anything. And overall, it's going to make your development process a lot faster. The sensors are plugged into an Arduino 101. And the Arduino 101 is being used as a sensor hub. Basically, we're just using it for its GPIO inputs as well as an analog to digital converter. All of the control logic is running here on our NUC. In order to be able to read that sensor data in, we're using Intel's MRA and UPM libraries. These libraries give developers open source sensor APIs that make reading in sensor data really simple. We cover all of this in much greater detail in our first webinar, and if you haven't already watched it, I'd recommend going back and checking it out. What this means in terms of data gathering is that you can identify what the important environmental data for your application is, and use inexpensive prototype sensors, as well as a simple API to read in all that data quickly and easily, and then send it up to the GCP machine learning service to start building up your ML model.
So now that you've got the data in the cloud and you're ready to go build a machine learning model, the question becomes, what is this machine learning thing, right? Machine learning engineers like to use really big words around concepts that really, when you sit down and sort of understand them, boil down to simple ideas, right? So machine learning is basically where you take data sets and then you apply algorithms to extract an understanding of data. So what used to be the case of, we had data scientists who worked on one data set or a few of them and like really understood the problem space, right? And spent years sort of being able to write these long SQL queries to go extract that right business answer. Instead, now we're saying, let's just throw this algorithm at the problem and use statistics to extract an understanding of this data, right? And that's all machine learning really is. So let's talk about what are the flavors of machine learning. Fundamentally at Google Cloud, we sort of see two audiences that use our tooling. On one hand, we have ready-to-use models. These are sort of general problem space models where things like you take a picture and you want to identify the kind of dog in that picture, right? And these models are trained by Google engineers using Google's massive scale and massive data sets. There's the same sort of technology that powers like Google Translate. So same tech, if you want it for your business, that's the ready-to-use models. Next up, we have an entire tooling pipeline to help you build your own models. And sort of the target audience there, it's data scientists, but there's the same folks who had that deep understanding of their data set to go build their own neural network based models end to end. So that includes things like scalable storage, scalable databases and warehouses like BigQuery, which sort of give you the same performance as your compute rises, right? And then we have what's called our cloud machine learning engine that lets you provision compute without sort of doing the management side of things. So you can literally say one line of code, hey, I want 10,000 cores to go run this in parallel, and we'll take care of that.
Okay, so if you wanted to recreate some of these pre-built models using the tools available, are they powerful enough to be able to actually recreate these models?
Definitely. So the tooling that we make available to you, like Cloud Machine Learning Engine, is inspired by the same internal tooling, the tooling we use internally at Google, right? So just like Kubernetes is inspired by Google's container management system called Borg, same idea of like Cloud Machine Learning Engine is sort of, we've gone through the hard part of how do you actually do these things at scale in production? And then we've brought the right pieces, the learnings to the table for you to just use. Right? So the short answer, yes, you can go rebuild the same thing as long as you have the right data sets. And that's sort of where the differentiation comes in, right? Is that for general cases that are like dog, cat, the example you always see, hot dog, not hot dog, right? Like that kind of like identifying the usual, exactly, like those general cases, our APIs do really well. When you're talking about things that are like, I took a photo of a part of my production line in my business, and I want to have a model that understands that, I think that's where you're starting to look into, okay, I need to build a model, I need my own data set to go do that. And that's where the tool chain part comes in.
Got it.
So going back to the machine learning APIs, we call these pre-trained models APIs because you interact with them as easily as you would any web API. These APIs make available to the public the machine learning sort of models that were built by Google experts. They're trained, as I said earlier, on our massive data sets, and heavy duty machine learning with thousands of cores is going on behind the scenes. But you don't need to learn any machine learning to use these. We currently have 5, more coming soon. So let's do a quick journey of the 5 of them. First up, the Vision API. This tells you information about images. You give it an image and it will detect and label it, saying, hey, here's a dog, here's an Alaskan Malamute in this picture. It detects faces and does sentiment analysis. So if you're thinking along the lines of, hey, when photos of my brand show up in a Twitter feed or along a hashtag, are people happy or sad? Do people generally correlate happiness with my brand? You can start extracting this, right? And then finally, it extracts text from images and flags inappropriate content. So if you're doing OCR at scale, you can use our API to extract the text and then get relevant business data back out of it.
And so once again, this was trained using the Google image repository, which is massive.
Right, and there's sort of this feedback loop going on there, right? Where the models are helping you find the images, which we're then using to make our original model even better. So it's a feedback loop that just keeps getting better and better. And you just have to use an API and you get the power of Google for your business case. So, all right, next up, natural language API. The natural language API is all about understanding text. It will extract and label important keywords. It does sentiment analysis, just like the face analysis. It tells you if the email you got to your support queue has a really angry customer, mad about your product, and you can prioritize it, right? Instead of auto-responding to the customer saying, hey, we will get back to you in 24 hours like we always, that your auto-responses, maybe you can send them back a coupon code saying, hey, we recognize that you're angry, we're prioritizing, we're sorry, here you go. And that potentially saves a lifelong customer relationship. Put it together, the API is useful for analyzing what people are saying about your products at scale. It helps you support multiple languages with advanced syntax analysis. So case in point, you get an email to your English support queue, but it's someone asking a question in Spanish. Instead of just saying, sorry, we only support English as a response, you can now come back and have at least a semi-helpful response, in addition to saying maybe we don't, do Spanish support directly. Next up, the speech API. The speech API is for voice recognition. It is the same core technology that powers Google Voice Search, Google Home, Google Assistant. We've put in billions of dollars of effort into building this, into internationalization, and we now support 80 languages. It is robust to noise, has a fast streaming API, so you can literally build similar scenarios as the Google Assistant. And you can customize it by passing it word hints. So if you have specific words that are common in your industry, you can have a tweaked version of the API that will understand that and sort of give you back the text result. Next up, the translation API. The translation API translates over 100 languages and thousands of language pairs back and forth between each other. We launched a premium edition of this a little while ago, and one of the breakthroughs Google has had in this space is earlier in the year, we started launching our deep neural network-based models for translation. So before that happened, everybody who was doing translation was primarily doing translation based using sort of phrase-based classical machine learning models. Google literally spends weeks and months training neural network models now, where we're getting to real-time translation. We're getting to the point where we can support the same accuracy as a human would be translating real-time. So there's some amazing stuff going on there. Next up is the Beta Video API. So at Google Next 2017 in San Francisco, we announced an ML API for extracting insights from video. The first set of this functionality lets you analyze a video across sort of the time dimension and say from a given timestamp to another, what is happening in a video. So you can say, hey, there is a tiger in this video from from timestamp X to X plus Y, whatever that may be. And so that's an API that we announced recently and we're continuing to iterate on. So expect more information on that soon. Putting all of that together, the best part of all of this is you don't need an account. You don't need to go set up anything. You can try these all in the browser. Literally just click, go. So I encourage you to play with them on your own. It takes 10 minutes to validate the effectiveness of everything that I just said. So go keep me honest, right? The barrier to entry is extremely low.
Right, and once you guys are done kind of exploring these in the browser, you might want to learn about how to implement them on the gateway. And as Karat said, there's really no reason to create your own custom model if a model already exists and it does what you need it to do. So as an example, let's take a look at how we can use that speech-to-text model to transcribe a piece of recorded audio on our NUC gateway. So for this example, we're going to be using the GCP SDK for Python to interface with the speech recognition model. Since the gateway does not come with GCP SDK by default, we're going to have to install and configure it before getting started. So we're going to install the Cloud SDK and then the Python module. We can do that by simply using apt-get for the Cloud SDK and then pip to install the Python module. Now, it's important that you initialize the SDK before trying to communicate with GCP. In webinar 1, we authorized our connection to the IoT core service by using a public-private key pair that we had to generate. Here we're going to be using the SDK to authorize access to the Google machine learning models. So no need for generating your own keys. You can do that from the command line interface. Basically run gcloud init, navigate to that URL that's generated, and log in. Once you log in and allow the SDK to access Google services, you can set a default geographic zone if you want. And that's all you need to do in order to set up and authorize the SDK. Once the SDK is set up, we can write our script that will send an audio file up to GCP for processing. The API itself is pretty simple. We basically import the speech package from google.cloud module, create a speech client, read in our audio file, set the parameters of that audio file, and then send the audio file to GCP for a response. Now keep in mind that there's going to be a few extra bits of code to make this all work, but in principle, this is all that you need. Also, in this example, we're sending a local file to the speech recognition model, but it's also possible to send a remote file stored on Google Cloud, or a streaming file using a microphone. Pretty powerful stuff that's wrapped up in a really simple API.
So let's get into the details of the latest wave in ML, the resurgence of neural networks. Neural networks are a construct built by connecting lots of perceptrons together, or neurons, if you will. A perceptron is just a function that has a conditional value. A perceptron can be designed to effectively host any mathematical function to calculate a value, right? That's all it is, really. So chaining together a bunch of these together lets us build complex, high-dimensional relationships in the model to capture from the data. A neural network ML model is just a structure of perceptrons with each layer performing a specific operation and then feeding its output to the next layer. In the case of TensorFlow, the actual asset is a model file that, once trained, is portable and reusable. The data scientist's job is to figure out the best structure of this ML model that results in a model that can capture the patterns, the statistical patterns within the data, so that you can then use that to predict future statistical patterns. That's neural networks. What is deep learning? Neural networks as an ML technique actually fell out of favor a couple of days after the original Minsky paper came out. And part of the reason for that was we did not have enough compute hardware to actually solve any real significant problems using that pattern. This has changed rapidly in the last decade or so, leading to the rise of deep learning. A deep learning model is nothing more than a neural network with lots and lots of layers. We're talking in some cases with some of the larger Google models now, millions and millions of neurons making hundreds of layers. There are multiple sort of ML techniques to train these deep neural networks. So let's step into sort of each one of them in terms of like, how would you train one of these large networks? So first up is supervised learning, or where you learn by example, where you have sort of, when you think about like, hey, I have a big data set where I know the right answer for each set of input problem data points, that's where supervised learning comes in. Second, there's unsupervised learning. Here you rely on the ML model to find and predict patterns in data where there isn't necessarily a right answer, right? An example would be by looking at people moving around in a store can you predict shoplifting, right? And to do that, you're effectively sort of trying to build clustering in terms of movement patterns of how people move in the store and see relationships form out of that, right? Third, sort of the most exciting ongoing research, right, is we have reinforcement learning. This technique utilizes trial and error patterns where the computer learns by actually doing the task. Again, while the core research in this space goes back decades, we're seeing a resurgence of its application and new groundbreaking research emerging now because of the availability of compute, right? Of the cloud in some ways, because that compute doesn't have to be pre-purchased up front. You, again, just get as much as you need for the period you need it.
Right. So, for instance, when Google Image Search returns something that you're not expecting, that's actually a way of it learning what it should be.
Yes and no. So that's actually a good point. I should highlight the difference, right? When I'm talking about learning real time, what I'm talking about is the case of think of it as a robot that I can teach to manipulate objects, where the robot isn't explicitly given a set of instructions of here's how you move an arm closer to the ball. The robot just is looking at a ball and its arm, and it learns. It's crazy as it sounds. It learns to figure out how to pick up the ball and put it in the hole, right? Like that is what we're talking about. What you're talking about is sort of a concept with that overloaded term called online learning, where real time, as humans give feedback to the pattern, like the model itself improves and knows that, hey, this picture that I thought was a dog is not really a dog. But that's not directly reinforcement learning. So another good example of reinforcement learning was it was successfully used by Google, the Google DeepMind team, to beat the top Go player in the world. The computer was able to figure out unconventional moves, right? People were watching the live stream. At that particular move, they all go, wait, that move makes no sense. Nobody should be doing that move in that particular case. And the computer did that because it could predict the outcome of the entire game all the way to the end. And that was taught by reinforcement learning. And that now has gotten better and better, where the computer played against itself to get better because there weren't humans that were good enough to beat it, right? So that's sort of where we are with reinforcement learning. All right, so let's talk about some common machine learning tasks. There's a list up there. Let's go through that. Classification. So dog or a cat. Going back to that example, what kind of bolt is this if it's a industry-specific model, right? Classes of objects and trying to figure out what fits where. Next up, regression. Think of it as you have a graph and you're trying to predict the direction of that line in the graph the next few steps, right? That's sort of what you're talking about. Then there's similarity, where I have a picture of a Alaskan Malamute. Show me pictures of more Alaskan Malamutes and not Siberian Huskies, right? That's sort of similarity there. Ranking. You see a lot of this and you go purchase something online, and how does the back-end system decide that it should show you what list of products, but not just that, but in what order, right? Which one should be at the top, because that's the highest probability you're going to probably, see it, click it, purchase it. So ranking. And then there is sequence prediction, where type ahead. So can I start pre-typing for you, right? Like what you see, your phone suggests the next few words in sequence prediction. Or again, the demo we're going to show, where can you predict the temperature readout of a sensor to then detect anomalies? And then the last, but again, not the least, dimensionality reduction, where say you have lots of options, you want to pick one or pick few. So this sort of goes hand in hand in some ways with the prediction, the retail example that I gave. Right? All right, so one of the core tenets of machine learning, right, is anytime you're trying to build a model, you'll end up dealing with cost functions. So this is sort of where we get into the nitty-gritty of the math of this, if you will. A cost function basically quantifies the delta between what a model predicted versus the truth or the reality that it's trying to model. The process of training a model is basically an iterative thing where you take lots of predictions from the model, you calculate this loss, this cost, if you will, right? I'm overloading terms, but effectively think of it like calculate that delta. And then you go back and adjust that model so that the inner sort of weights, if you will, of the model are adjusted to reduce that loss. And then you start again do it again with the next batch of data and the next batch of data. And as you can imagine, hundreds of thousands of these iterations later, the model gets very good at given a set of inputs, it gives you that set of outputs. So how do you reduce this loss? One of the ways to reduce loss functions is to use an algorithm called gradient descent. I'll skip the mathematical details of the algorithm here, but for one point. The algorithm itself is relatively simple to implement, but implementing it across multiple machines to build a modern large-scale model is very hard. You have to solve all sorts of problems and challenges around managing the cluster, connecting them together, all of that craziness. TensorFlow makes this easier, while also providing other scenario-specific reduction algorithms, right? That, again, I'm not going to go into detail here, but you have a list of choices where one might be better than another depending on the exact model, right? And that's where the data scientist comes in. You can use these pre-built models and algorithms and libraries around TensorFlow to make your engineering process easier so that your devs and your data scientists and your business people can work together to solve the business problem and the data science, and not necessarily the how do I bring a set of machines together to work together to solve an algorithm. Now, let's say you're along your journey of building this model. One of the things to be very careful about is overfitting. No model is 100% accurate. Building a good model involves trading off between multiple metrics to prevent, again, overfitting. Overfitting is where the model, after training, is over-specialized for the training data, but not generalized enough to be useful for new data. One of the techniques used, for example here, is regularization, which imposes additional cost on model complexity. My higher point here is that in this space as well, there are some high-level things that your data scientist has to be aware of, but there's some programmatic things that you can do as well. And TensorFlow has tooling for you to go do that in a way that says, hey, call a couple of functions, and then it takes care of that problem for you. So this goes back to the larger set of choosing the right tools and not building them all. So as you can sense, there is a theme here. Let's talk about the theme, the tools, right? You don't build your own library for measuring time, right? The Y2K bug, like go back 2 decades. The reason that happened was everybody was writing their own date calculation function. And it's complex and it's hard. And you know what? There's no business value in doing that. So instead of going to do that, rely on something that does the mundane for you so you can solve the high value problem. So why TensorFlow then? There are other options that have lots of libraries as well. Well, here's the thing. Of the other tooling chains that are available, TensorFlow is the most popular. This right here is a measure by GitHub stars. We have massive amounts of public contribution. We work directly with the community and is the fastest growing sort of community platform for machine learning today.
So is a model that's trained in TensorFlow compatible with the other tooling frameworks?
Actually, yes, it is. So let me give you an example. The Keras API is a higher level API that lets you sort of simplify even some of the dialects that TensorFlow uses to build certain kinds of models. That API is something, for example, Apple now supports in their Core AI platform. Core ML, I'm sorry. So you can train using Keras. The end result is a TensorFlow model, but this can now run on an iPhone in Apple's stack. So one of the core tenets of the TensorFlow design was you could swap out the underlying execution environment, but the model itself is a self-contained asset that can run anywhere. So previously it used to be you would deploy something like Spark and then have an algorithm you wrote that trained a model, but then portability was sort of an afterthought, and this was put right up front. Actually, that sort of brings me back to the point of why is it so popular, right? Because it's flexible enough for research, but performant and portable enough for production. It's very rare to have a single framework that does both of these things well. Traditionally, you'd model your problem on a developer-friendly framework, and then you would come back and sort of your production team would say, okay, we get the math of this, let us write this in a way that actually scales, right? TensorFlow takes care of that because the model lets you go from sort of an environment where you're sort of IDE iterating, coming up with maybe this model works better, and then just taking that asset and running it in production. The popularity of TensorFlow also means that you'll have a vibrant community of fellow developers to reach out and get for help. which, for example, Stack Overflow, we've got, like, our engineers are reaching out and working with this community. So if you do get stuck on something, we're there to, we or the community is there to help. All right, so let's get into the specifics of the model we built here, right? We built what's called an LSTM. It's a long short-term memory. It's a deep neural network pattern where the model can effectively build the concept of a memory. It's not a stateful machine per se, but it has the concept of taking a set of data points from the past and then being able to predict the next data point because it can look at a sequence in the input data. This pattern is often used in situations where there's some periodicity to the data, right? There's a rhythm, maybe there's a sequence, any of that. And that's what makes it a great fit for detecting anomalies and streaming IoT sensor data because there's a periodicity, right? Your temperature goes up, goes down, there's a rhythm of business that applies, and an LSTM can learn that. So how does that work? The way this works is that the model is trained by giving it a set amount of time slices of data and getting it to predict the next few steps. Then, so when you're doing that over lots and lots of time slices of data. Then at runtime, similar inputs are provided real time, and the model predicts the next few data points. These next few data points are then compared to the real world measurement using multiple methods like thresholds, accumulators, and Gaussian techniques relying on variance. Once the delta between the model prediction, what the model thinks should be happening, and the real world triggers whatever your threshold algorithm is, your measure is, now you have an anomaly because over the set of the clean data you trained it on, that didn't happen. So let's say you had a temperature sensor and it expects a gentle shift in temperature and there is a fire. Well, the temperature is going to shift really fast. It's going to trigger an anomaly, right?
So basically the difference between it getting warmer throughout the day versus it spiking up.
Exactly. And then the more sophisticated you get with the actual detection side of things, so there's a prediction and then the detection. And there are techniques like you can use a neural network itself for the detection side of things. But putting all of that together, what it helps you do is instead of the old system of setting a threshold of if it gets above 90 degrees Celsius, there's probably a fire. Instead of that, let's say your server room does get hot. It has big swings in temperature for whatever reason, right? Just hypothetically. Your model understands that. So it doesn't just trigger every time there's, an event that is expected to happen on the third Tuesday of every month or something like that, right? You can train that into the model.
Right.
All right, so let's jump right into the code here. What I have in front of me is Google Cloud Data Lab, which is a version of, it's an open source version of the Jupyter notebooks, which have been modified to just make it easy for you to do things like push jobs into Google Cloud, like solve the authentication challenges and things like that. All right, so what's on screen right now is my folder of code files that is used to train this model. There is the model file, model.py, which defines the TensorFlow graph for the model itself. The setup file, as the name indicates, is setting up dependencies, things like that you may need installed on the at-scale machines. And then finally, there's the task file, which manages the multi-machine process of like, how do you get this model on multiple machines? Let's go through each one real quick. First up, this is the model file. I'm not going to step through the details of each piece of code here. We will be sharing a blog post at the end of this video that has all of this really well detailed. But I want to take a moment to highlight that some key pieces here that come into play. The recurring theme that I kept sort of harping on earlier was don't use the building blocks that exist for TensorFlow, don't rebuild them. This is a very good example of that. In creating the TensorFlow graph, to build an LSTM, you should not be starting from connecting bits of neurons together. That doesn't make sense. Instead, what I'm doing here is using the basic LSTM cell that TensorFlow already provides. To simplify my tasks, I can just connect together bigger and bigger pieces to solve the larger problem. That's part of the model. Next up, at a higher level, the task file, which does the orchestration. Instead of, again, managing the execution and split of the data across hundreds of machines, what we're doing here is using the TF-Learn estimator API. This API takes care of all of those sort of difficulties for you so that you take the model, you point it at data, and you say go. And the estimator API takes care of slicing up the data sets, running them in parallel, and combining the results for you. Again, another example of not reinventing the wheel yourself. Now that the code's ready, you need to run it. That brings me to this other piece of code here that actually starts the cloud machine learning job. And what's happening here is we're taking those files, combining them into a task called trainer.task in this case right here. And we're telling Cloud Machine Learning Engine, hey, run this in the region I defined here, US Central 1, with these other parameters and at this scale. This knob about setting the scale for your job is something you control to say how many resources you want to run this training on. For example, I've run trainings where I've literally requested thousands of cores with a similar config file, and it will give that to me and I won't have to do any management, and I will only pay by the minute. So once you submit the job becomes a machine learning engine job, which you can on the Google Cloud Console track as it's running, look at the logs, all of that. And then finally it tells you how many ML units it consumed at the end of the job so that you always know what each specific training event costs you. The output of this job is a trained model, which was set, we set the target output directory as a flag. That's what this directory looks like. And there's a bunch of extraneous files here, generally concerned around resuming training and all of that. The file in question here is the graph.pbtext. This file is the entirety effectively of your TensorFlow model, including the structure and the weights and all of that. So now that you have that, Cloud Machine Learning Engine also has a way to, just like it had a training job, has a way to host files for you in an auto-scaling platform, so you never have to worry about how do I, actually use this model. So let's move over to a cloud function that I have written that lets you, every time there's a new temperature reading from the device, this function gets triggered. What it will do then is grab the last 9 readings from BigQuery, going back to sort of the work that was done in webinar 2. That data is then used to predict what should be the 10th reading according to the model. So we asked Google ML Engine to create that prediction based on the model we had given it. That prediction is then compared to the actual 10th prediction that triggered this function. We look at the delta, in this case a very simple threshold, and if the threshold's exceeded, we log that there was an anomaly. Again, in this case, you could do whatever other action that was needed in the case of an anomaly. So this was running in the cloud, but with IoT, you might not have good low latency, reliable connectivity. How do you solve for that? And the way you do that is you move the model closer to the edge, onto your gateways, onto your edge devices. So Martin, you want to talk about that a little bit?
Sure. What we can look at here is a bit of a hybrid model where we train our ML model in the cloud using the Google Cloud APIs and then run that model locally on the gateway. So like you mentioned earlier, training a ML model requires a huge amount of compute power and way more than is going to be available even on the highest end gateway type device. So we can offload that task to the cloud where we have access to all that power. We can set up the sensor data, we can run the training, and we can generate a training model. So instead of running that model in the cloud, we can run that model locally. And running the model locally means that you have to set up your compute environment locally. And you're also going to have to be limited by the compute power that you have available on your local device. However, the trade-off being that you are no longer bound to the cloud service to run your model. So let's say that our application uses an ML model to run a real-time control system of some kind that has a low tolerance for any kind of latency. In that case, by running the model locally, we can avoid having to deal with any latency issues that can arise from leveraging a planet-scale cloud analytics platform like GCP. Likewise, if we're using our model to run a control system, we don't want that control system to stop functioning completely if it loses connection to the internet. I can imagine something like this being used for, let's say, monitoring a train that can pass through regions without internet connectivity, or just go through a tunnel and lose service completely. Once again, if we run the model locally, we won't have to worry about losing our control system if we lose connectivity. Finally, there can be an issue of the amount of raw data that is being fed into our model. In this example, we're passing in a single temperature reading once a second, which is a fairly trivial amount of data. But we can imagine an application where we actually have to send a non-trivial amount of data to the model for processing. If instead of a single reading once a second, you have to send 100 readings or 1,000 readings once a second, you can start to run into bandwidth issues. So once again, running the model locally, we can get around those issues. So that's kind of the reasoning behind why we might want to run a trained model locally, and let's just take a quick look at how we can do that on our gateway. We can run our trained model on a local instance of TensorFlow. And since our gateway is running Ubuntu, and TensorFlow is an open source platform, there's really no issues installing it and getting it running. You can get your environment set up in a few ways. So first, you can use pip to just install the Python modules in the user environment. We can also use a virtual environment to create an isolated Python environment and install TensorFlow inside that. And finally, we can use Docker to install an entire isolated Docker image with TensorFlow installed inside. I would say that if you are running many Python applications on your gateway, that an isolated environment is the preferred way of going. But if you're only running TensorFlow, the simpler local install is probably what you would want to do. Now we're ready to run our model. When training our model, we generate a protocol buffer file, or a .pb, which contains the graph data about our models, as well as the weights, the gradients, the biases, basically all the information that we need to recreate that neural network. By loading this file into TensorFlow, we can rebuild that model that was trained in the cloud, and then start passing sensor data into that model. It's going to monitor the sensor data and predict what it thinks the next temperature value is going to be. And we can load all these parameters into TensorFlow using a load module API. Once the model is loaded, we can run our temperature data array through the model. We read the temperature data using our sensor API temp.read. And then we run our model. The model is going to output a predicted next temperature value based on 9 previous temperature readings. We can compare the predicted value to the actual reading and decide if that delta is high enough to label it as an anomaly. Now keep in mind that we're going to have to match the data format that the model was trained with. So we're going to have to pass in an array of 9 temperature values every single time in order to get an output for the 10th value.
All right, so that's all we have for today, folks. We hope that this session really helps you start solving real business problems with machine learning. Start your journey, get machine learning implemented into your business.
Yeah, and thank you again for tuning in. And I really hope that this whole series of webinars really inspires you to go out and create IoT solutions for yourselves. We'll see you guys next time.
All right, welcome back. Hopefully the material in that recording was helpful to you. So we've collected some questions along the way that came up in the live chat and otherwise. So let's just jump right into them. The first one was, how much data do you need to train a model like this, particularly around LSTMs? So the way to think about the data requirements are, think about the periodicity that you're trying to build into your model. So for example, if you have a temperature sensor in a room that is very climate controlled, that has very narrow ranges that don't change a lot, then you need a short window of data to train this model, and then it will detect anytime there is an anomaly. If you've got, say, a temperature sensor inside a refrigerated truck that sees significant shifts in temperature, right? The air conditioning's turned off at night when it's parked, all of those things. Then you'll need more data over time as this truck travels, the United States or whatever it may be, to build that periodicity back into the data. Cool. So there isn't a strict sort of megabytes, gigabytes, terabytes requirements, more about what you're trying to model. Cool. So.
Here is another one. What kind of sensors do the Intel sensor library support? The UPM sensor library supports about 400 different sensors and actuators, from low end all the way to like industrial commercial grade sensors. You can monitor like variety of environmental variables, temperature, pressure, gas, moisture, and so on. And over different kinds of protocols as well, Wi-Fi, Z-Wave, Zigbee, BLE, USB, Modbus, etc. So take a look at upm.mraa.io, and you'll get a lot more information about what these libraries can do for you.
Awesome. All right, next up. So what are some good resources to learn modern machine learning and deep learning? So I'd say a couple of things to do. Number one, Coursera has a few courses on deep learning. But what I'd suggest you do is you start from the older sort of machine learning course that's available on Coursera. What it'll do is it'll help you build a good foundation around what are the sort of traditional techniques that were around before neural networks came along and became more popular, not even came along, became more popular, and then how they're related. And then from there, you can do the deep learning course that was recently launched on Coursera. And I think that's a very good sort of ramp up to then figure out where you want to go deep, because if the field is really wide and really deep. The other thing I would add is Google has what we call code labs available. So if you just search TensorFlow code lab, one of the first results should be a code lab that is for TensorFlow without PhD, without a PhD, if you will. And that's a great start because it gives you a very quick rundown on everything you learned from the Coursera course, how it applies to what look real TensorFlow code. So that's where I would say you should start.
Cool.
All right. So the next question I think is this one's more relevant for what you're covering, which is is it one model per sensor, right? Or is there a way to build a model for temperature sensors across a facility? So
go ahead.
Sure, I can take that one. So the way I think that you should think about that again is it's not one model per sensor, but what you're again going back, especially in an LSTM kind of pattern, what you're trying to build is a coherent model of what's happening in the real world over time. So you could do one model per sensor if you're deploying this on each sensor and then do some training at the sensor. Or the other pattern is collect groups of sensors that observe a connected environment in some sort. That pattern works really well. So again, if you have sensors across a warehouse, you can take all of this data and effectively, where I was putting in the code, you saw basically a vector of temperature measurements for one sensor. It would be a matrix of measurements across time, and then you could train a model that way. But again, sort of start from the perspective of what environment am I trying to model, and then go from there, and then pick the right tool for the job. All right.
So I want to use a microphone to do streaming video or voice to text locally using a NUC. What's the best way to do that? That sounds like an interesting project.
Yeah.
So one way to do it would be to pick a microphone that has support for Ubuntu, right? Pick a microphone that has like a USB support and then plug it into the NUC. You'd also want a recording software to record the audio and then send the audio chunks to the Google ML API. In the webinar, and if you're sticking with Python, you can use PyAudio. That would work. And then you can chunk the audio and then send them to the ML APIs. But one thing that I'd recommend is make sure that the samples are long enough. So I'd probably say about 100 milliseconds or longer would be a good idea. But good luck with the project.
Yeah. And I'd add one more thing. The API supports both synchronous and asynchronous audio. So if you want to do something like a Google Assistant scenario where it's like live happening right in the moment, you can use the synchronous API, or you can use the asynchronous API for larger chunks of audio, pre-recorded audio that you're trying to transcribe. So it works both ways. All right, next up is what are the resource requirements to run TensorFlow at the edge in a scenario like this on an edge gateway? The way I'd answer that is, I think the pure number people think about is, oh, I can measure flops. It doesn't really work that way because model complexity drives, and the model type itself drives a lot of your resource requirements. So what I would say is figure out the problem you're trying to solve. At a sort of small, medium, large budget of like, hey, I'm running a big server at the edge versus I'm running a low power device. Like start from that. That sort of gives you a constraint on, am I doing hundreds of thousands, millions, or hundreds of millions of neurons, right? You're starting to think like that. And then from there, benchmark and iterate. And what you'll find is that if you had done a flop space measurement, it doesn't scale linearly, because as your compute at the edge goes down, different bottlenecks show up, like memory bandwidth and things like that, that impact how well the model runs.
Yep.
And then the other side of the equation is also think about, if you don't need your inference to happen in 30 milliseconds, then that really frees you up in terms of how much compute you need at the edge. We have scenarios where we've deployed effectively a Raspberry Pi, and it runs super slow, but it was good enough for that scenario, right? 6 seconds to do inference, but that was good enough for what we were doing. So think of it that way, and then test and iterate, and then shrink your model as and when necessary, trading off accuracy, basically your F1 score against the compute requirements. So, all right, looks like
that's all the questions.
That's all we had. So, thank you for joining us on this webinar. And again, if you have any more questions, do post them at the bottom of the video. We'll come back around and try to answer all of them as well. Thank you for joining us, and we'll see you again soon.
Thank you.